Chapter 11, gases. This is one of my favorite chapters, so that's good news for today. Extra long straws. You know, my kids were actually doing this. We went to Taco Bell the other day, and they were actually doing this, sticking the straws together. And, you know, to see how long of a straw that they could make. And apparently the author of the book did this as a child too. And here's an interesting question. How long is too long when making a long straw for drinking? How does a straw work? Do you ever think about that? When you suck on the straw, you're removing some of the molecules from inside the straw, and you're creating a pressure difference between the inside and the outside of the straw. And the straw, the liquid, the soda, is actually pushed up by the straw, in the straw, by the pressure on the outside of the straw. So this child is sucking on the straw, he's taking air out and changing the pressure inside versus outside. The outside pressure then pushing on the soda is what causes it to go up the straw. Now, obviously, when you're sticking straws from a fast food restaurant together, they leak where you join them, and they're really flimsy plastic, so that's not going to work the best. But even if you had a perfect straw, the walls were rigid, there were no holes in it, it turns out that if you got longer than about 10.3 meters, which is 34 feet, the straw would not work. Even if you pulled a perfect vacuum on it, you could not get soda to go up any higher than about 34 feet. It's interesting. Why? Question?
Well, what if it was, just curious, what if it was like a metal straw? Same problem?
Even a metal straw wouldn't work. I mean, you could be pulling a vacuum on it. The soda or the liquid would actually start to boil before it would get above 34 feet.
I thought that you couldn't maintain the pressure differential.
Well, it would be difficult, but it can be done. Not with your mouth, but like if you had a vacuum pump, it still wouldn't work. Still wouldn't work. It's interesting. So hopefully when we get done with this chapter, we'll understand a little bit more why. So there's a pressure difference between the inside and the outside of the straw. The pressure is the force exerted by gas molecules as they collide with the surface. So in the air, there are gas molecules, and they collide with surfaces, and that exerts a pressure. At sea level, the average pressure is 101,325 newtons per square meter, or 14.7 pounds per square inch. Now, pounds per square inch is probably a unit of pressure you're more familiar with. If you've ever had to put air in your bike tires or your car tires, the unit is going to be PSI, pounds per square inch. So when we suck on a straw, the pressure inside is less. There's less gas molecules inside because you sucked them out, and there's more pressure on the outside. So there's this pressure outside exerted by the atmosphere, 14.7 pounds per square inch. Even with a perfect vacuum, it can only push soda up to about 10 meters, 10.3 meters. Because at that point, the column of soda or water, this guy apparently really liked orange soda, exerts the same pressure as the gas molecules outside do. And so the pressure then is equal inside and outside, and the soda won't rise any farther. Yes?
Essentially, that's what I was saying. You couldn't say 34 feet or whatever it is, equalize it so you can't maintain it. It won't go any higher.
Right. The pressure exerted by the soda, even though there's a vacuum up here, is equal to the pressure outside.
Right. So
yeah.
what I was saying was a differential just not, you can't create that.
Yes. I thought you were saying that you couldn't maintain the vacuum.
No, I was considering even external forces like
Yep.
pressurized systems.
Yep, that's exactly right. I guess that's the end of that section. Anybody have any questions about that? It's one of those everyday life things that you probably didn't really think about before.